So in chapter 13, we studied vector functions, right? And how the way a vector function worked is it would be like r of t, right? Position as a function of time. Now what we're going to deal with is vector functions that depend on a location in space, right? So if you give a point in an xy, or if it's like a 3D grid xyz, then a vector field, I should say, is because this is what the topic's about. A vector field is just a vector function that maps a vector to a point in space, right? So an xyz, or an xy, depending if you're in 2D or 3D. So for example, for part A, if we think about f of xy, this vector function is defined as y I hat plus x j hat. So let's try to draw this out, right? First of all, you notice, well, at f of 0, 0, right, at the origin, let's just focus on the x-axis right now. So for the origin, 0, 0, that would just be a vector, right, with the 0 component in the x direction, 0 component in the y direction. That's just like a 0 vector, it's nothing. Now, if you think about like f of 1, 0, right, if we move 1 in the x direction, then your x component, this is a little bit counterintuitive, right, just because of how the function is defined, it's y I hat, right? So the x component is just your y value. Well, your y value is 0, so there's going to be no component in the x direction. Now, what about in the y direction? Well, it's x j hat, right? So the y component is the value of x, which in this case, right, if at f of 1, 0 would just be 1. So if we were to draw it, it would be a vector that looks like this, right? It would be at that point, right, I'm drawing the vector at 1, 0, and it has 0 component in the x direction and 1 component in the y direction. And then you could see, well, if you go 2, 0, right, this is still, the x component is still 0, but the y component, which is the x value, is going to be 2. So you get something like this. Now, usually you don't want to draw them this big because there are going to be other vectors. So what I'm going to do, should I leave it like that? We'll make it a little bit smaller. So we'll make it something more like this. But just know that they get bigger. They get progressively bigger along the x-axis. And then you can imagine what it could look like for the y direction, right? Or as you go up the y-axis. Now, your y value is just the x component. And now your x value is a y component. And because x is going to be 0, there's going to be no y component. So it's going to look kind of like the opposite, right? It's going to kind of look like that. And then you can start to imagine that, okay, well, if you were to go along this sort of diagonal, right? If you were to start going along like 1, 1, 2, 2, 3, 3, right? Those would just be vectors with components like so, right? It would have components that are causing it to be diagonal, right? A component 2 to the right and a 2 up, or 3 to the right, 3 up. And then, right now, for kind of the in-between, you would think like, okay, well, if you start, if you start going up from the x-axis, you're gonna start having more of a, like for every point along, let's say a certain axis, right? Like x, this is like x equals 2 or whatever. At x equals 2, right? The y component's always gonna stay the same, but then as you go up, the x component's gonna start getting bigger. So it would be something like this, and then you would get something more like this, and then you get this sort of vector field going, right? So it would kind of look like this. I'm pretty bad at drawing them, but you can hopefully see, right? You would get a vector. I'm probably drawing this terribly. Let me show you what it would look like, because I'm just trying to get an idea of how you can think about these, right? You just map them according to, or you draw the components according to the coordinates, right? So y of x, if it's going to load, yep, there we go. It will look something like this. Hope you could see. I was kind of getting there, right? It would look like that. That would be the vector field, right? So that's all a vector field is. You can see a vector field, right, is just a bunch of vectors in space, and the components of the vectors are like following this kind of rule. That's all a function is, right? It's a rule that says, hey, if you put an input, there's going to be an output, and the output instead of being a scalar value, is just a vector value. So now if you think about in the 3D world, it's very similar, right? It's just going to be, when you start mapping this out, right, at the origin, there's nothing. And then if you actually think about this one, right, the x component is the x value, the y component is the y value, and the z component is the z value. So if you really think about it, right, imagine a point x, y, z right here. Well, this vector would really represent, from the origin to this point, right? But because, we're plotting it, we're really plotting it at that point, right? Vectors, they don't depend on the starting location, right? It's just the direction and magnitude. So you can just draw, this vector will be the same no matter where you draw it. So really, it's going to be a vector drawn at that same point. I just erased it, but at x, y, z, right, it would look something like this, right? It would represent the vector, right? If this was a point right here, you could just say, like, I kind of like to draw them at the middle, right, as you kind of noticed. So if you think about it, all these points, right, if you think about all the points, the vector function just represents the vector from the origin to that point. So you would just draw that vector at that point, right? So if I think about this point, that's going to be the vector, so it's going to kind of look like this. So you're going to notice that, hey, all the vectors are going to be kind of pointing radially outward, right? There's going to be that radial symmetry. And let me actually show it to you. All right? It's going to look something like this, right? There's going to be that radial sort of symmetry. So hopefully that kind of makes sense, right? Like, it's going to have that radial symmetry in this kind of special case because the x component is the x, the y component is the y value, the z component is the z value. Now for kind of a last example is, what if you want to graph the gradient? We'd actually, talked about the gradient before, and really, if I want to find the gradient, remember, as a refresher, the gradient of any function, so gradient f, is really just a vector with the x component being partial f, partial x, plus partial f, partial y for the y component, and then so on for how many variables the function has. This is just a vector. This is just a vector field, right? We call it the gradient vector field. So I can actually solve, the partials in this case are easy, right? Partial f, partial x is going to be 2x, right? You treat the y as a constant. And then partial f, partial y is going to be 2y, right? So the gradient is really going to be a vector with components 2x and then 2y. And remember, if you have a point like xy, really, this vector would represent a vector with components xy, right, going from the origin to a point xy. But this vector is going to be double, right? It's going to be double that in magnitude. It's going to be kind of double the length. And we're plotting it at that point, right? We're not plotting it here, we're plotting it at that point. So it would look like this, right? Or if you had a point right here, it would look like that. Or if you had a point like here, it would look like that, right? Because it's just this vector, right, from this point to this point, but double the length. And then you just plot it at that point, right, instead of at the origin or whatever. So you would imagine now you're also going to get radial symmetry. If you graph these all out, and you can imagine, it's going to have that spherical kind of symmetry, because if you imagine, or I guess circular symmetry, because if you imagine a circle, the distance, right? So if you think about a circle, the distance from a point xy, for all points along that circle, I can just draw it out just to make it more tangible, but the distance is all the same, right? So the distance is all the same. So that means the magnitude of a vector xy would be the same. And this is just 2 times that vector xy. So all points along the circle, they would have the same vector magnitude. So it would have that spherical symmetry. So if you can, and I can just show you that it would have, let me just show you what it would look like. It would look something like this. Right, circular symmetry, not really spherical. So yeah, if you've been following along with the book, I would just encourage you to look at the examples and see what kind of vector fields are there, right? You could have, this could be sine x times I plus ln j, right? And see what kind of vector fields different functions can make. But yeah, this has been vector fields, not a crazy concept. Another thing to note is, hey, if you can, a vector, so here's the deal. The gradient actually, okay, how do I explain this? I believe, I'm pretty confident that if a function, f of x, y, can have a gradient, right? Gradient f, this is actually a conservative field. And a conservative field, what does that mean? We'll see. We'll see how, what a conservative field really means. But if you've ever heard of the fact that a conservative force, right? The electric force and the gravitational force, well, those are actually gradients, right, of their potential energy functions, or their potential functions. And so if you know the electric potential is kq1 over r, you can actually derive an equation for the electric field by taking the gradient, and it would end up being a conservative field. So yeah, I just wanted to point that out. But yeah, thank you for watching this lesson.